This talk is about quantum cognition, and Stuart Hameroff gave that an introduction yesterday in his talk. This is a new field that's sort of taking inspiration, and in particular taking the mathematical structures from quantum theory in order to try to model cognitive phenomena more effectively and to provide new insights into how to model cognitive phenomena. So rather than give you all a broad brushstroke of what quantum cognition is doing, I'd really like just to focus this talk on one aspect of cognition where we at the University of Queensland, Queensland University of Technology, have been applying mathematical methods from quantum theory to model a specific aspect of cognition. So let's start with a motivating example. So if you see this conceptual combination, right, what's the first thing that comes to mind? Right, so you might think of dried pieces of apple that you eat like potato chips, or you might think of a chip in a computing device from the Apple Computer Corporation. Or perhaps something a little bit more obscure, like you might think of some chip used to grow apples more effectively. Right, so all of these are perfectly valid interpretations of the conceptual combination apple chip, which is being seen without context. The question is, from a cognitive point of view, how do we ascribe meaning to such novel concept combinations? So this is largely, even though this has been studied in cognitive science, it's still largely an open problem about how we do it. So one of the ways that we could think about doing it is via the principle of semantic compositionality. This is a very, very powerful principle that originally came out of the field of logic, but has a deep footprint in a number of fields ranging from linguistics to computer science to cognitive science. So it's good that we've got Jeff Pelletier on hand, who's a philosopher, who very succinctly describes this principle. This principle of semantic compositionality, sometimes called Frege's principle, because it was Gottlob Frege who purportedly put this principle down, is the principle that the meaning of a syntactically complex whole is a function only of the meanings of its syntactic parts, together with the manner in which these parts were combined. Right, so this is very, very succinctly described, this principle. Now, we have been asking the question whether conceptual combinations such as apple chip are semantically compositional. So one way to think about this principle is it's articulate the whole is somehow a sum of the parts. And what we've been doing, we've been applying probabilistic methods that have come out of quantum physics to address this question. So let's go deeper into this principle of semantic compositionality. Now, why would this be a principle applicable to how we ascribe meanings to conceptual combinations? So this is, once again, we have Jeff Pelletier on hand, and there are a number of reasons, but this is perhaps what I think is the most powerful. Compositionality is the only explanation of how a finite mechanism, such as the human brain or mind, can understand an infinite set of sentences. So we know in language there are an infinite number of possible sentences. So without compositionality, novel utterances, say like apple chip or things you hadn't seen before, would not be understandable. So we derive the understanding based on the constituent parts that we've seen before, and then we pull them all together cognitively to come up with the meaning of this novel combination. So that's a powerful argument for semantic compositionality, and that's one of the reasons why it has such a deep footprint in the number of fields that I mentioned, because it is a very, very powerful principle. What about arguments against compositionality? There are several. These have come from within cognitive science, but also within philosophy, and particularly in relation to these conceptual combinations. So let's look at another conceptual combination, pet fish. So what is the first thing that comes to mind when you think about a pet fish? Well, often in studies, the subjects think about something like this, a goldfish or a guppy in some sort of bowl. Now, one of the important developments in cognitive science is prototype theory. And the argument against compositionality goes like this. The prototype of pet fish cannot result from the composition of the prototypes of pet and fish, because a typical pet, when we think of a pet, that concept on its own, that's something warm and furry, like a cat or a dog. When we look at when you do the studies of what's a prototypical fish, it's often something greyish, like with grey scaly fish that perhaps you eat. But notice that pet fish, the prototypical pet fish, is neither furry or warm nor greyish. So it's impossible or very, very hard to see how the prototype of pet fish can be composed from the prototypes of these other examples. So that's an argument against compositionality. So now I'd like to move on to some preliminary intuitions, and then I'll go on to about how we can sort of start to address this question about compositionality. Now, if we're trying to probe, if we're trying to understand about how humans cognitively deal with words or concepts in memory, one method to do that is via free association experiments. So this is data that's now old. It's probably a couple of decades old, from the University of South Florida word association norms. So these Doug Nelson and Kathy McAvoy are empirical psychologists that we work with. They've normed a large number of words across English words. So how these experiments go, like subjects are given the word apple, and they're asked to report what's the first word that comes to mind. And if you do this over a number of subjects, you can ascribe a probability. So you can see them here. So red is an associated word that comes up quite strongly at probability 0.21, orange, fruit, pie, worm. Those first four deal with the fruit sense of apple. Down the bottom you see computer, which is dealing with the computer sense of apple. Now, I would suggest if we did those experiments today, where there is a larger proliferation of Apple devices, you probably would see the computer sense of the concept Apple coming more into this association norms. So, but what we can see by doing this, by probing the human mental lexicon like this, we can see that it suggests that Apple has at least two senses. We've got a fruit sense, and we've also got a computer-related sense. So that allows us now to model Apple as a superposed state. So one of the reasons I've been put this up, there have been a number of researchers in the quantum cognition area who've more or less independently came up with these sort of quantum-motivated or quantum-inspired representations of words in memory. So what we can see here is we have here a basis vector here which corresponds to the computer sense of Apple. And then we have another one down here, a basis vector that corresponds to the fruit sense. So what is hypothesized? Before the human subject is probed by the free association experiment, they're cognitively in this superposed state between the two senses. When they're asked to report an associate, then what happens is then they'll produce an associate like worm or pie, which relates to the fruit sense of the word, or they might produce computer, which relates to the technological sense of Apple. So what we're trying, I guess the intuition or the analogy we're trying to work with here is that when we're looking at a concept like Apple, it can have certain polarizations. So it can polarize in a certain way like a photon. It can polarize in its computer sense, or it can polarize in its fruit sense. And the sense here is, or can be equated, these basis vectors can be sort of thought of as axes of possible meanings of this word or concept. Now, moving on. So what we're going to do is we're going to run now with the intuition that we're going to model these conceptual combinations as interacting quantum systems. So how do we do it? So what the physicists do, and we've heard this story a couple of times during this conference, you can prepare these twin state photons, and what you do is you let them drift apart, and then so at one end, down this end, you'll set a polarizer. You'll set a polarizer down at the other end, and because when the photon interacts with the polarization measurement device, then it might polarize as up, signified by +1, and at the other it might polarize down, signified -1. So then what you can do is you can reorient the polarizers, and it'll be +1 down this end, and it might be -1 down the other end. So essentially, this is the very high-level description of how these experiments are conducted with twin-state photons, and when they're trying to confirm entanglement, for example. Now, how do you do this? How would you do this with conceptual combinations? Well, this is what we came up with. So we're now saying, okay, we have these two concepts, apple chip. We're sort of running with this analogy that they're like interacting quantum systems. So what's the analogy of the polarizer? So for one end, we've got apple. So one of the things we can orient the human subject is via priming. So what we first do is we show them the word banana. Without showing them the concept combination, they first show them the word banana, which orients them towards the fruit sense of apple. On the other side, we would have, say, potato. This potato orients the human subject towards the food sense of chip, like potato chips. And then what happens is we can... So if the subject indeed interpreted the apple chip according to the primes, they might come up with something like this, dried pieces of apple that you eat. So that would be a ++. So you can do this again. So we'll prime prime the computer sense of apple with the prime word computer, and then we will prime the circuit sense of chip with circuit, the technological sense, and then we can sort of measure how the subject interpreted. In this case here, it's a -1 because even though they were primed to interpret apple in the fruit sense, they ended up interpreting it in the technological sense. So it's -1 or down. So this is an example of what a subject produced. A nano-chip Granny Smith. So a Granny Smith is a variety of apple. So what you see, the primes set the context. They do not determine the outcome. So this is the same in the quantum physics experiment. They're just setting the context, setting the human subject, oriented in a certain way by the primes. Then we give them the conceptual combination. We ask them to write it down. And so this is an example, a nanochip Granny Smith. And subsequently, we ask the subjects to declare specifically, did they interpret apple as a fruit or as a computer or something else, or chip as a food or circuit or something else. So we collect that data. Now, so to just orient your expectations with respect to this talk is not about adjudicating the debate between compositionality and non-compositionality. So this debate has been going on quite a while. In fact, probably you could see that with the definition of semantic compositionality. It's actually quite underspecified. So what you see in the literature is that there's quite a lot of debate about where the dividing line is between compositionality and non-compositionality. You get different varieties of compositionality. You get weak compositionality, strong compositionality. These are all signs that the actual principle is somewhat underspecified. We're not entering into that debate. What we are putting forward is we're presenting empirically driven analytic methods for determining a clear boundary between the two. And the contentious aspect, I guess, is that the methods come from quantum theory. So the onus for us and its legitimacy hinges on how well we can translate these methods from quantum theory or quantum physics into cognitive science. So let's look at the analysis of non-compositionality or compositionality. Now, what I've got here, I'll take you through this. So this is a grid of probability. So I'll take you through this because this is important to understand some of the latter analysis methods. And it's even though it's abstract, it's really easy to interpret. So here we have our concept apple. Here we have the other one, chip. And these are the priming conditions. So here we prime the fruit sense of apple and then the food sense of chip. Here we prime the fruit sense of apple and the circuit sense of chip. And we've got the computer sense of apple and the potatoes, or the food sense of chip, etc. So you have 4 priming conditions. So we prime one group of subjects with banana and potato, And what we do is we measure how they interpret. We measure the plus and the minuses, how they're interpreting the combination. So up here, P1 represents the probability that they indeed interpreted apple as a fruit and potato as a food. P4, would, for example, would be where even though are primed to interpret apple as a fruit and chip as a potato, that they didn't. So remember, they were not forced. The primes were just orienting them in a certain way. But that doesn't determine the particular interpretation that comes out, exactly as in when they're doing the experiments with twin-state photons. And so you have 4 probability distributions that are in these represented by these colours. So these would be all different groups of subjects and the probabilities that there are different interpretations came out. So that's the framework. So this is the basis. This is the basis not only in quantum physics but also what we've been doing for conceptual combinations for analysing compositionality. So how can you do this? So first we'll make it a little bit more abstract so we don't talk about individual words. So we'll call A and B as our concepts. A1 is priming one sense of concept A, A2 is priming another sense, B1 is priming a sense of concept B, and B2 is another sense. And then what we can do is, okay, we assume Apple responds with +1 yes or -9 no when probed with A1 banana or A2 computer, similarly for B chip. So this is just, once again, a rehash of how we do the priming and how we generate the interpretations. Now here we go. So now suppose, now this is the step. So now suppose that we adhere to semantic compositionality. So how do we express that? Or how can we possibly express that in terms of this probabilistic framework? So one possible way would be, so we've got our this joint distribution here on the left-hand side is representing the model of how the concept combination is being interpreted. Now let's assume compositionality. You see, you don't need to be a mathematician to see this. We have one probability distribution based on concept A and another probability distribution that's hinged on concept B. And these are conditional probabilities of the priming, but that's a technical detail. But you see how this is the whole, and now we're trying to express that whole as in terms of its parts. So that's one form of compositionality assumption. So this is, the physicists do this too. Well, we took the lead from the physicists. So these are a number of different papers that are in this area of analysing the compositionality of twin-state photon systems or entangled systems. So this is from the Clauser-Horn papers, and this is from Shimony 84, Maudlin 94, Feyns 2003. We see the same pattern. So this is the whole. This is the model of the photons of the conceptual combination, and we're trying to express it in terms of these individual parts. So express in whole and parts. So you see the whole is the joint probability distribution. That's the left-hand side. And the compositionality expressed mathematically is how this joint probability distribution factorizes. So you see we've got a factorization based on the A and another term based on the B. So that's how compositionality is expressed in terms of that mathematical framework. So this is all physics, but does this at all play out in cognitive science? Well, let's give an example of that. So there is a well-known model by Gajny and Shobin from 1997 that which was a model to try and explain conceptual combinations. And so their hypothesis was that when people interpret a novel combination such as Mountain Magazine is because the availability of relations is determined by the relation frequency of the modifier mountain. So this is, when you in conceptual combinations, the left concept is called the modifier, and the right-hand one is called the head. So they're saying that there are relations that are unspecified in the conceptual combination, but cognitively they're active. So, for example, let's see, so mountain goat is easier to interpret than Mountain Magazine because the located relation is more often used with the modifier mountain. So we'd think that the goat is located on the mountain because that occurs more frequently rather than Mountain Magazine because this is a magazine about mountains. So that was the basis of their model. So how would you express that? Once again, we see this would be the joint probability distribution trying to model how these are interpreted. We've got this variable R that represents the hidden relation. And you can see here that we have this term here where we're working with the joint probability of the interpretation of concept A with the relation. that's getting back to this assumption that the availability relation is determined by the relation frequency of the modifier mountain. So this is the probability that takes that into account. And then here we have the interpretation of concept B. So that's an example of how you could do that, how that's done in cognitive science. Once again, we're trying to understand this combination by breaking it down into its parts. Now, a legitimate question is that why would you express compositionality as a factorization as a product? And there has been some literature about that. So it was a physicist, I think John Bell, I think was the first that actually did it in the case of the photons. Now, you could say, well, there might be other mathematical means to formalize compositionality. So after all, we often colloquially express the whole as the sum of the parts. Right? So why wouldn't you use addition to express compositionality? Well, this is where Feyns Theorem comes in. So this is if I would want to leave you with a very, very important result that we've discovered in our research, and this is Feyns Theorem that came out from a Journal of Mathematical Physics in 1982. Now, I wanted to show you the theorem, and I'm not expecting you to be able to read this, but I want to take you through this theorem, and I also want to leave with you why this theorem is so very important and how it can be applied to cognitive science. So here we have A1, A2, B1, B2. Well, we've seen those before. So A1 and A2, B1, B2, these correspond to the random variables over +1, -1, which says, well, have I seen apple interpreted as a fruit or not? Have I seen apple interpreted as a computer or not? Have I seen chip interpreted as a food or not? Have I seen chip interpreted as a circuit or not? So we can empirically collect that data. But all we need is these 4 variables that are modeling how the concept is being interpreted. The next thing here is we have these pairwise joint distributions. So these are the ones that we've collected. Right? We've collected these from the human subjects, and we've asked them. So they were the 4 coloured grids we saw in that matrix. Now, then we get this, then the necessary and sufficient conditions. So mathematically, what this colloquially means, this is as good as it gets. A theorem that provides both the necessary and sufficient conditions is the strongest result that you can get. And what is it? It's the necessary and sufficient condition for this joint probability distribution to exist. This is our model. This is our model, what we're trying to construct of how these conceptual combinations are being interpreted. So we're constructing this model as a joint probability distribution over those 4 variables. And Feyns gives the necessary and sufficient conditions for this to exist. Right? And so this is the dividing line. This is our position on the dividing line between compositionality and non-compositionality. And there are a couple of things to remark about this. The first is this theorem is based on standard probability theory. So you see nothing in here about photons. You see nothing in here even about distance. It's a general probabilistic argument that we feel that can be taken outside of quantum physics and applied, in our case, to cognitive phenomena. So the other thing, so I'll leave the other remarks to as I go through. So back to our framework, and we can retranslate these grid of 16 probabilities in terms of Feyns theorem by stating the variables A1, B1, B2, A2. This is how the concept, the apple, is being interpreted with a fruit or not, as a computer or not, chip as a food or not, or as an electrical circuit or not. So that's our structure. So Feyns Theorem 3 asks the question whether the joint probability distribution, this is our model of S, can be constructed from our data. So this is what we collect from human subjects, and the physicists collect by doing these experiments and firing photons on both sides of the analyzing apparatus and collecting the +1, -1 results. Now, the striking thing is that this model S is non-compositional. Why? Because you can't model S in you can't model a system in a single probability space. So colloquially, that means you can't decompose something that doesn't even exist. So this, for me, that's come from computer science and more recently done work in cognitive science. This is an extremely striking result. because when you're developing models in these fields, what do? You say, what are my variables? The probabilistic model I see, what are the variables? And then you make judicious choices about what these variables are. And once you've done that, you have a joint probability distribution. You never ask yourself the question whether this joint probability distribution exists or not. You never entertain the idea that it may not exist. So I think this is one of the striking developments that have come out of quantum physics. And also I think Feyns Theorem is a beautiful mathematical result that opens up us the question about whether in certain situations we've hit the absolute limit of what our modelling can do. So when the joint probability distribution doesn't exist, then you've hit a very, very harsh, stark barrier. And that's why we say this is a very, very good dividing line between compositionality and non-compositionality. So let's do it. So we did the empirical evaluation. So this is just a summary of our experiment. So we took 65 psych undergraduate students. The procedure was a single factor design. That's just all detail. But what's specific in our case, we had to develop a special double priming method. Because remember, we have to, just like the physicist, we need to sort of almost like perform measurements on the concepts or prime them simultaneously. So we developed a cognitive procedure to do that based on other work that had been in the literature which were close to doing something like that, and we developed it further. There are two analysis methods. There's the Clauser-Horn-Chimney-Holt inequality, which I won't talk about here, and Feyns Theorem, which I will talk about. So this is the result. So these are our concept combinations down here: Boxer-Back, Bank-Log, Abel-Chip, Stock-Tick, Seal-Pack. So you can see that all of these have this same character. So when you think about boxer, you could think about a boxer as being a sport, or boxer, at least in Australia, is a quite popular breed of dog. You've got bat, which can be an animal, but it can also be an implement used in sport. Like in India, we know cricket bats are very popular, as they are in Australia. So you can see that both concepts are ambiguous, and they're brought together, and these are fairly sort of novel combinations. So boxer bat, bank log, apple chip, stock tick. Here we see the priming words. So for apple chip, we saw banana priming the fruit sense, computer priming the computer sense of the word, potato priming the food sense, and circuit priming the electronic sense. Now, so when we look at apple chip, we see here that it violates Feyns Theorem. So just to say something about the statistical analysis, the physicists have the luxury that they can run millions and millions of photons through these measuring devices. So we've got 65 subjects. We can't run 65 millions or millions of subjects to do this experiment. So what we do is we develop this method from statistics where you can bootstrap samples. So we have a sample of interpretations that have been collected from 65. We can bootstrap new samples in a statistically justified way. And so we bootstrapped 2,000 examples, 2,000 new experiments based on this. And what we see is that 100% of those bootstrap samples violated Feyns Theorem. So there is a very, very strong reason to believe that apple chip is non-compositional. That means we cannot construct this joint probability distribution, this global model, across how it is being interpreted. And also you can see down here there are quite a number of different, the bolded ones, are a number of conceptual combinations that show this non-compositional character defined as we define it here, as a violation of Feyns Theorem. So I'd like to conclude this talk. In my abstract, I promised to say something about some relation of this work that we did with Bohm and Hiley's intuitive understanding of non-locality. So I'm not a physicist, so I'm a computer scientist and a cognitive scientist, and I've started to read numerous papers. And along the way, I found this particular one from Bohm and Hiley is a very, very interesting paper. So on the intuitive understanding of non-locality as implied by quantum theory. So it came out in 1975. And I corresponded with Hiley on this paper, and he actually said he felt that this is one of the better papers that he and Bohm had written. And it relates to what we've been trying to do with conceptual combinations in the following way. So this is a quote out of the paper. we bring out the fact that the essential new quality implied by quantum theory is non-locality, i.e. that a system cannot be analysed into parts whose basic properties do not depend on the state of the whole system. Right, so if we recall back to the principle of semantic compositionality, this view is at odds with the intuition behind compositional approaches like semantic compositionality, where we can actually come to an understanding of the whole based simply on the function of an understanding of the constituent parts. And then they introduce this notion of unbroken wholeness, and this is just a piece taken out of the paper. It denies the classical idea of analysability of the world into separately and independently existent parts. And they do that in terms of this three-level system. So you've got a supersystem, a system, and a subsystem. So let's just try and ground the intuitions behind that. So this is taken out of Bowman-Hiley's paper. So an example of a system is a superfluid. A system might be a helium atom, and then underneath the helium atom you've got the electrons, protons, and neutrons. So that's how they divided up those three levels. And this is what they have to say. Thus, when we describe a superfluid, and that's in this case the supersystem, as constituted of helium atoms, we have not reduced it to a set of helium atoms. So we haven't reduced it into these individual bits. Right? And because the interaction of these atoms are still determined by the state of the whole supersystem. Similarly, the helium atoms, this is now the system, is made up of electrons, protons, and neutrons, which are from the subsystem. But the behaviour of these depends on the state of the helium atom as a whole. Okay, so that's how they bed down how these supersystem, system, and subsystem are to be understood. Now, how is that related to what we did? So this is actually, it can be carved up in this way. So at the supersystem, we have this mental lexicon. You can think about this large network of word associations that we hold in memory. At the system, we've got a particular conceptual combination, and subsystem, we have the constituent concepts. Now, this is actually what, in 1975, what Bowman-Hiley wrote. They said that this view can be applied to numerous other phenomena outside of quantum physics. And specifically, they mentioned concepts. So they said, mental phenomena, example, the relations of two concepts depend crucially on broader concepts within which they are comprehended. So I would say how we translate how they view broader concept. The broader concepts here is this human mental lexicon, but also, most notably, how that's been subjected, the state of the human mental lexicon as it's been primed, or after it's been primed. That would be our supersystem. Then we have the conceptual combination, and the behaviour of the concepts depends on the state of the conceptual combination as a whole. Right? So notice that semantic compositionality would be the other way around. Its behaviour is determined solely on the basis of its parts. So we feel that what we have done here is actually is somewhat of a confirmation of what Bowman-Hiley were thinking about way back in 1975. So this is a good time to close. So some parting thoughts. The violation of Feyns Theorem suggests that conceptual semantics and human cognition is not necessarily compositional. So we feel we've demonstrated that there are specific conceptual combinations that violate Feyns Theorem, and then, according to our definition, they are non-compositional structures. So what is the implication of that? So that means a purely reductive approach to modelling cognitive phenomena is thus brought into question. And this is Bowman-Hiley said, what quantum theory shows is that this form of wholeness is appropriate not only to biologically, socially, and psychologically, but is also even for understanding the laws of physics. So this is a bold, pioneering stance, I feel, and this talk substantiates it from a psychological perspective. And also, I might add, there is a community of researchers worldwide, of which I am part, that are taking quantum physics and using that, and particularly using the mathematical structures of quantum physics to apply to problems outside of what we traditionally understand as physics. So this particular view that Bowman-Hiley had in 1975 is actually quite a driver for this particular quantum interaction community that exists now. And finally, quantum cognition, I'd like to leave you all with an impression about that more broadly. we have found that it can be applied to model a wide variety of cognitive phenomena. So what we're learning about in this journey is it's not always a straight application of quantum theory. There are some adaptations that need to be made along the way. So we have disjunction and conjunction effects in probability judgments. That's my colleague Jerome Bussemeier, with whom we wrote this book, has done a lot of work in this area. Violations of the distance axioms and similarity judgments. Violations of the sure thing principle in decisions. This is what I talked about, modelling cognitive phenomena in a non-reductionistic way. Over and under extension effects found in relation to membership judgments of conceptual combinations, bistable perception of ambiguous figures, and more lately there's been some work on using quantum theory to model social attitudes, both internally held by the human agents and more as expressed more globally in society. Thank you for your attention.
Have you been able to measure, or could you measure within the experimental paradigm you're using, reaction times to see whether reaction times for reaching a decision were the same or different in situations that were either compositional or non-compositional?
Yeah, so we recorded all the reaction times, and that's something that we're going through now, because we've got this paper under review and that's one of the things that they were interested to see, to hear about. But what we see is that there are differences in reaction times in terms of their interpretations. And I think it's easy to see how that, because sometimes because we have certain biases about how concepts are going to be interpreted. So, for example, if you look at the norm data, to interpret apple as a fruit is very, very strong. So we have quite a strong predisposition to do that. But when you put the priming when you put the primes at odds with that predisposition, that engenders a longer interpretation time because it's somewhat odd.